The last equation of the previous lesson gives another proof of adiabatic invariance and tells us on the way how accurate the invariance is. The abbreviated action is not a single-valued function of the coordinate, but the extra quantity is, because the differentiation is at constant action variable and the many-valued increments cancel. Being single-valued, it is a periodic function of the angle variable, and the mean value over a period of the derivative of a periodic function is 0. Averaging the equation, with the slowly varying rate taken outside the mean, leaves the mean rate of change of the action variable equal to 0. Now for the accuracy. Let the parameter tend to constant limits long before and long after, and let the action variable be given at the start. The question is how much it has changed in total by the end. That total change is the integral over all time of minus the derivative by the angle times the rate of change of the parameter. The quantity is periodic in the angle, so we first expand it in a Fourier series. Provided the parameter varies slowly enough, the angle variable increases monotonically with the time, so we may change the variable of integration from the time to the angle without altering the limits. Now treat the angle as a complex variable. Assuming the integrand has no singularity on the real axis, we push the contour up into the upper half-plane. The contour is caught on the singularities and forms a loop around each of them. Let the singularity nearest the real axis be the one that matters. The main contribution comes from its neighborhood, and every term of the series brings an exponential factor. Keeping only the slowest decaying term, the total change is of order e to the minus its imaginary part. Let the corresponding complex instant be the point where the angle takes that value. Its magnitude is of the order of the characteristic time over which the parameters vary, so the exponent is of order the frequency times that time, that is, the time divided by the period. Since the characteristic time is far longer than the period, the exponent is large. The slower the change, the more exponentially small the total drift of the action variable. To leading order, drop the small correction and integrate the frequency up to that instant.